Good morning. And if you are watching this via a video without me here, I had to be in Chicago over the weekend and made this video so that we wouldn't fall any further behind than we already are because of the weather. This lesson is called Variations, and it actually draws from two different sections in the book. Section 2.2 is about a particular kind of variation, which is called a direct variation. And section 8.1 has inverse variations, which we're already familiar with. And it has something called a joint variation, and then all different combinations of variations. So, and these are all the SOLs that are related to it. So it's fairly important in terms of SOLs, and it doesn't quite fit in with any of the things that we've done before or after. It kind of stands alone. So the first two kinds of variations that we deal with are called direct and inverse. And they have these formats. The direct variation is y equals k times x. In this equation, the variables are x and y. K is a constant. We don't know what it is as we start the problem, but it is a constant. It's not a variable. Variables vary. They change their values, or they could take on many values. K is a constant. For example, I could say y equals 2x. Okay, that's a direct variation. The constant, this k is called the constant of proportionality. And you might even see in this book they might call it the constant of variation. So direct variation, y equals a constant times x. In an inverse variation, it would be y equals a constant divided by x. Again, just for an example, I could say, let's say that's y equals 2 divided by x. Now, the way I like to think of it is, if it's a direct variation, x and y vary in the same direction. Meaning, if I double x, I'll double y. If I cut x in half, I'll cut y in half. Right? Because they're at the same level on both sides of the equal sign, they're both in the numerator, right? As one changes, so does the other. They vary directly. For an inverse variation, because one of the variables is in the numerator and one of them is in the denominator, that's not true. Right? If I make the denominator of a fraction bigger, it actually makes the whole fraction smaller. Or if I make the denominator of a fraction smaller, it makes the whole fraction bigger. So again, when x goes up, y goes up. And this one, if x goes down, y goes up. Right? They vary inversely in different directions. So we'll leave that at that. That's the basics. That's what we mean by direct variation and inverse variation. In fact, they're both functions that we've dealt with so far. Right? Back in chapter 2, that was the chapter where we're reviewing linear functions. And this is a linear function. I mean, you could think of it like y equals mx plus b. Just in the direct variation, there is no b. And instead of calling the constant m, we're calling it k. Right? So in the end, it's just a linear function with a y-intercept of 0. This one, y equals k divided by x, or y equals 2 over x. We actually did that at the beginning of Chapter 8, what we did with Chapter 8. If you remember, we started out in Section 8.2, which were the graphs of inverse variations. So now we are dealing with the inverse variation, the function itself, not the graph. So those should be familiar with us, or to us. So in order to detect whether data represents a direct or an inverse variation, you got to see if it fits the pattern. You know, is it a y equals kx or is it a y equals k over x? The first clue in this one, notice as the x's get bigger, the y's are getting smaller. So which kind of variation might that be? That might be an inverse. Okay. If it is an inverse variation, then we would expect y equals k over x to be the relationship. And if I solve that for k by multiplying times x, then I get x times y equals k. Meaning, if every time I multiply x times y, I get the same number, a constant, then this is an inverse variation. So let's see. Is this column here, x, y. 2 times 15 is 30. 4 times 7.5, that'd be 28 plus 2, 30. 10 times 3, 30. 15 times 2, 30. So in every case, x times y is a constant. It's 30. So this is an inverse variation. And the specific inverse variation function that it is y equals 30 over x. So is the relationship direct, inverse, or neither? It is inverse. Write the function that models the variation, y equals 30 over x. How about these? As the x's are getting bigger, looking under this column, right? The y's are getting bigger. So if it's anything, it's a direct variation. So in order to tell for sure, I know a direct variation, y equals kx. If I divide both sides by x, I get y over x equals a constant. So if y divided by x in every case equals the same number, then I know I have a direct variation. So I'm going to make my other column here now, y over x. Okay, 8 divided by 0.2 is 40. Is it? Go ahead and do the math, but yeah, 8 times 2, it should be 40. 20 divided by 0.5, 40. 40 divided by 1, 40. 60 divided by 1.5. Again, you have a calculator, so just put it in the calculator and you can tell. If you're not sure, I can do this. I can say 60 divided by 1.5 equals 60 divided by 3/2 equals 60 times 2/3. And the 3 goes into 60 20 times, and 20 times 2 is 40. So in fact, every time I divided y by x, I got the same number, a constant, 40. So this is a direct variation. And the function is y equals 40 times x. So direct and inverse variations. And those kinds of problems are interesting, but they're not the kind of problems you are going to get when you're asked questions about variations. This is the starting point of the kinds of questions you're going to get, and we can show this. It says using a proportion, so I'm going to use a proportion to solve this. But generally, these problems are presented in 3 steps. Okay. One, what kind of variation? In this case, suppose y varies directly with x. Okay, that's step 1. It's a direct variation. 2, since we know it's a direct variation, we know that it would match this equation. They've got to give you next a point where you know both the x and y values so that you can solve for k. So substitute given point. Solve for k. So in this case, that would be right here. They're telling you when y is 9, x is negative 15. So let me plug that in. 9 equals k times negative 15. And so we should solve for k. Divide both sides by negative 15. You get k equals 9 over negative 15, which is negative 3/5. Okay. So once you know that, we're going to substitute that. I said 3 steps, but it's okay. Substitute into this equation right here. So now we know y equals negative 3/5 times x. And then 4, there's always a question at the end. Answer the question. Okay, if y equals negative 3/5 x, how can we tell what y equals when x equals 21? Well, you can substitute 21 for x, right? Because you know k already, then you'll be able to solve for y. Plug in y equals negative 3/5 times 21, which is negative 63/5. These kind of go together right there. But let's say that those go together. We'll call this step 3. Step 3. So first, they're going to tell you what kind of variation it is. Second, they give you a point where you know the values of all the variables at that point, so you can solve for k. So you do that, and you've got a new equation where the k now is known, and then you answer the question. These kinds of questions come up in SAT kind of things all the time, and it's always asked in the same way. For the SOLs, they will either be asked exactly this way, or they might just ask you, after getting to this point right here, they might say, what is the value of the constant of proportionality, or the constant of variation? So you would just stop at this point here that you found k equals negative 3/5. But one or the other. Now, I did say I was going to solve this like a proportion. So just to show you that, let me do that. So since this is a direct variation, and I don't particularly like to solve these this way, but maybe it'll help. A direct variation, y equals kx, means that y over x equals a constant. So what that means is that if you have 2 different points, then you can actually think of it like this. y1 over x1 equals y2 over x2. I mean, the sub one, y1, x1, y1 is 1 point, x2, y2 is another point. So what I would do is I would substitute. The y1 is this. There's y1 and x1. So I'm going to substitute 9 divided by negative 15. And this is going to be the x2, and this is the y2, which we don't know. So y over 21. So we're using this relationship here to say it should be that for every point that y over x is the same thing. So just set it up like that, right? Y1 over x1 equals y2 over x2. That's a proportion. That's something you can solve by cross multiplying. So when you do that, you'll get 9 times 21 equals negative 15 times y. So we're going to get y equals 9 times 21 divided by negative 15. So y equals, and we kind of already know where this goes, right? Because we're going to divide a 3 out of 15 is going to give us 5, and 3 into 9 is give us 3 sets, 63 sets. So this is using a proportion to solve a direct variation. So you go ahead and try the same thing here. And since it was a solve with a proportion, you are, free to solve it as a proportion. And if I was you and you're watching this, and hopefully you've got a substitute which is controlling the pause button, you might hit pause right now and just stop, or stop the video. I'm going to go ahead and solve it now. So pause before you watch me solve it. Okay, so if I'm going to solve this using a proportion, again, what I'm saying is y1 over x1 equals y2 over x2. In my problem here, y is 15 when x is 3. So that's x1, y1. Find y when x is 12. So that'll be, so just substitute for those numbers. 15 over 3 equals y over 12. Cross multiply. 3y equals 15 times 12. So let's see, 15 times 12, 12 times 12 is 144, plus 36 is 180. 3y equals 180, y equals 60. Okay, inverse variations. Similar kind of problem. Suppose x and y vary inversely, and x equals 4 when y is 12. What is the function that models the inverse variation? And then what is y when x is 10? So in a way, again, the step 1, they're telling us what kind of variation that we've got. Step 2, they're giving us the value of 1 point where we know both the variables. And step 3, they're asking us a question. So let's see. I can do like this. Y equals k over x. Substitute. Y is 12 when x is 4. 12 equals k over 4. Solve for k. K equals 4 times 12, which is 48. So now that I know the k, I can substitute. Y equals 48 over x. Step 3. What is y when x equals 10? Okay, so we're going to substitute that 10 there. Y equals 48 over 10, which is 4.8. Okay. Now, again, I could have done that different. I could have done a similar thing to what we did when we solved with the proportion. Right, since this is a inverse variation, then y equals k over x. Therefore, x times y equals k, which means x1, y1 equals x2, y2. And remember, our x2 is going to be 10. So we set that up. 4 times 12 equals 10 times y. 10 y equals 48. Y equals 48 over 10. 4.8. Now, I don't like to solve direct variations with a proportion or inverse variations like that, because we're going to deal with a lot more kinds of variations, and that will only work really that cleanly for those two variations. But this pattern here of defining your variation, substituting a point so you can solve for k, and then answering a question, that works for everything. And I personally would solve everything that way. It'll help you deal with all the kinds of variations we deal with in this class. It'll help you when you take an SAT, which will definitely have the same kind of problem. Okay, here's another U-try. So for the U-try, if you want to go ahead and get started on it and have the substitute or whoever pause this while you work on that, it'll be paused. I'm going to go ahead and solve it now. Suppose x and y vary inversely, and x equals 8 when y equals negative 7. Okay, so y equals k over x. X equals 8 when y equals negative 7. Negative 7 equals k over 8. Therefore, k equals negative 7 times 8, which is negative 56. So y equals negative 56 over x. So what is the function that models the inverse variation? That is the function. What is y when x equals 2? Y equals negative 56 divided by 2, which is negative 28. So there's one other kind of variation that we're supposed to know by name, and that is called a joint variation. And a joint variation, we need 3 variables for this one. Z varies jointly with x and y. And you can see from the equation that the z is on one side, and the product xy is in a direct variation with z, meaning it's at the same level. As xy goes up, z goes up. If xy goes down, then z goes down. So this one is called a joint variation. Now, they've given us a couple others here, but in fact, these are just 2 examples. There are many, many other kinds of variations that you could do. Well, let's see how this one reads. Z varies jointly with x and y and inversely with w, okay? Z varies kxy, so there's the joint part of it, and the inverse with W means the W is in the denominator. Okay, Z varies directly with X and inversely with the product of WY. So it's direct with X, which means Z and X are at the same level. They're both in the numerator. And the product WY is in the denominator, inverse with the product WY. And you don't call that a joint variation when it's in the denominator. It's only a joint variation when it's in the numerator. But you could have, you could say Y varies directly with X squared. Z varies directly with X squared and inversely with Y to the third. Z varies jointly with X, Y, and inversely with W to the fourth power. I mean, you can come up with any number of variations like this, and you will see different kinds. You're probably never going to see something as easy as here's a direct variation or here's an inverse variation, solve it. It's almost always going to be more complicated than that. So keep in mind, there are infinite number of possibilities of variations. Okay, and what do they all have in common? What do every one of these that you see here have in common? And the answer is they got a constant K. So remember, when you're writing the equation for any kind of variation, it's going to have a K in it. Okay, K, K, K. K for kickpan. So here's how we solve any old kind of variation: direct, inverse, joint, any variation thereof. First, we're going to identify the type of variation. Then we're going to write the equation for that variation, including the K. We're going to substitute for the variables with the given point, and we'll solve for K. Then we'll substitute for that K in the equation that we generated after step 2, and then we'll answer a question if there is a question to be asked or answered after that. So this one, the number of bags of grass seed, N, needed to reseed a yard varies directly with the area A to be seeded and inversely with the weight of the bag of seed. If it takes 2 3-pound bags to seed an area of 3,600 feet squared, how many 3-pound bags will seed 9,000 square feet? Okay, so the variation, we have N varies directly with A and inversely with W. So let's write that down. N equals K A divided by W, right? So that is identifying the variation and writing the equation that includes K. Okay, substitute for the variables with the given point. Okay, so they have to have then given us where if it takes 2, that's N, 3-pound bags, that's W, to seed an area of 3,600 feet, A. Okay, they just gave us the values of N, W, and A all at one point. So we're going to substitute for those and solve for K. So it's 2 equals K times 3,600 divided by 3. So let's see. 3 times 2, 6 equals 3,600 times K. So K equals 6 divided by 3,600. And just to make that simple, 6 goes into 3,600 600 times, right? 6 times 600 is 3,600. So that is we substituted for the point, we solved for K. So here's our new equation. N equals 1 over 600 times A over W. You kind of don't even need the 1 there, but that's okay. So we substitute it into that equation. Now 6, we can answer the question. The question is, how many 3-pound bags will seed a 9,000 square foot area? So how many, that's the n, will seed a 9,000, and in the denominator we have 600 times 3. So n equals 9,000 divided by 1,800. And if I'm not mistaken, that is 5. Okay. So here's your chance to try the same thing. And I know it's complicated, but that's one of the reasons why I put these steps right here. So go ahead and pause the video and give it a shot. If you're having trouble, you might let the video go ahead one step at a time, see whether you can at least get the next step. So we'll go ahead and pause now. Okay, in this one it says the number of bags of mulch you need to cover a planting area varies jointly with the area to be mulched and the depth of the mulch. Okay, so the variation is the number of bags you need varies, and when I say the word varies, I write down K. Right? Oh, don't forget the K. It's one of the number one mistakes that I see when we do variations. Is what you set up in the beginning doesn't even have a K in it. Okay, it's K. It's a joint variation with A and D. So that was these two right here. Check. Okay. If you need 10 bags to mulch 120 square feet to a depth of 3 inches, how many bags do you need to mulch 200 feet squared to a depth of 4 inches? And I will say this. So although it doesn't really matter, we have an issue because they're giving us, one of them is in foot squared, the other one is in inches. And I'm going to just like play fast and loose with that, and we'll just leave it in the units that it's in because it's not going to make any difference in the end. Okay, so here we go. The one point they've given us, you need 10 bags to mulch 120 square feet to a depth of 3 inches. So they gave us the point, substitute 10 equals K times 120 times 3. So this will be K equals 10 divided by 3 times 120, which is 360. So it's 136. So here's our new equation. N equals 136 times AD. Right, that was this and these two together. Now that we know the K, we can answer the last question. How many bags do you need to mulch 200 square feet to a depth of 4 inches? So substitute the 200 and the 4. N equals 1 over 36 times 200 times 4. N equals, the 4 goes into 36 9 times, so that's 200 divided by 9. And, you know, we could divide that, and that'll be 9 goes into 20 2 times with 2 left over. That'll be another 0.2 and 0.2 repeating. So it's like 2 1/5 bags. So that is the lesson, right? These are, again, are the essential learnings from the SOLs. We're supposed to understand what it means to say y very jointly as x and z, y equals kxz. We're supposed to know what it means to say y is directly proportional to x, y equals kx, and inversely proportional, k over x. And then given a situation, determine the value of the constant of proportionality, set up and solve problems. Okay, that is it. And the homework comes a little bit from section 2.2, which was only about direct variations, and then the rest comes from section 8.1, which includes direct variations, inverse, and all the different combinations.